Stanford University.
Okay, let's go back to, I'm going to try to, we've done this before incidentally, but you know, there's only so much physics out there and I can't keep making it up fast enough to, I wish I could, but I can't. When I was younger I could. So we're going to do things that we've done before. All right, let's go back to what we learned about the geometry of a black hole near the horizon. Near the horizon, we found out that it was just pretty much good old flat space-time, approximately, very, very close to the horizon. And we described it by a particular metric. For this purpose, we started, of course, with the good old Schwarzschild metric, but we made a bunch of changes of variables. In particular, instead of the Schwarzschild coordinate r, there's never enough ink here. Instead of the Schwarzschild coordinate r that goes into the Schwarzschild metric in the usual way, we replaced it. Oh, good. We replaced it by another variable, which was actually the proper distance from the horizon. R is not the proper distance from the horizon, but rho is. That's its definition. That's the definition of rho, proper distance from the horizon. And I won't bother writing down the relationship between them. Not terribly important to know. But rho, one thing is important, when at the point when r is equal to 2mg, that's the Schwarzschild radius, that's the point where the horizon is, at that point, rho is equal to 0, proper distance from the horizon. Right. We also made another change of variables. Omega, which is a time variable, was equal, and it's a dimensionless time variable, is equal to the Schwarzschild time divided by 4mg. So roughly speaking, in every place here, c is equal to 1. C is equal to 1. Roughly what omega is, time and length are measured in the same units when c is equal to 1. 2mg is the Schwarzschild radius of the black hole. So apart from a factor of 2, omega is time measured in units of the Schwarzschild radius. So that's what omega is, and that's why it's dimensionless, because it's a ratio of things, time divided by the Schwarzschild radius. And when we did that, we went through a little exercise. It was a number of steps, more steps than I really like to do, but nevertheless, we did it. And we found out that near the horizon of the black hole, we call it the near horizon geometry, that the proper distance was equal to minus rho squared d omega squared. I can write this in terms of proper time. The difference between proper distance squared and proper time squared is just you change the sign. You can write d tau squared and put a plus sign here. The omega squared plus d rho squared. And then there was another piece coming from angles on the horizon, but I'm not terribly interested in that. I'm interested in distance from the horizon and time. A two-dimensional picture of the black hole. Just time and distance from the black hole. Okay? This is what the metric is like. And then I pointed out to you that this metric is very, very similar to the metric of ordinary flat space, conventional flat space, the surface of this table here, in polar coordinates. In polar coordinates, we would ordinarily write, I don't want to write it here because I don't want to confuse it with this, but ordinarily in polar coordinates, theta rho, we would write that ds squared is equal to rho squared d theta squared plus d rho squared. So they look very similar to each other. The only difference is this minus sign, and omega is analogous to theta. It's a hyperbolic angle. Just to finish, yeah, all right, that's good. This is flat space, ordinary flat space. This happens to be nothing but ordinary flat space-time in a kind of polar coordinate reference frame. Everybody remember this? And omega is T over 4mg. Now, this is the metric close to the black hole horizon. We draw a picture of this. This is just flat space in polar coordinates. So it looks something like this. Omega is a kind of hyperbolic angle variable, which way down the remote past, omega is equal to minus infinity. Way up here, omega is equal to plus infinity. And rho, lines of constant rho, are just hyperbolas which look like this. And here's the horizon. Right over here is the horizon, or right over there. If we come in along a line of constant omega, fixed time, that point right over there is r equals 2mg. It's rho equals 0, but it's r equals 2mg. So that's what we set up last time. We also said that the horizon of the black hole, well, the general horizon, there's two notions of horizon, incidentally. One is called the bifurcate horizon. I'll tell you the words. The bifurcate horizon is simply this point over here. And the bi, I don't know what furcate means, but bi means two, and the two-ness are the intersection of these two light cones here. That's called the bifurcate horizon. But there's another notion of horizon. The other notion of horizon is a more physically interesting one. It's this whole light-like surface here. Why is that interesting? Well, if somebody gets stuck behind that light-like surface, they cannot send a message to the outside. They cannot send a message out beyond that light-like surface. So this is a kind of horizon, and once you're behind it, you can't get any information out to distances beyond the r equals 2m, or r equals 2m, or rho greater than 0. Okay, so that's the geometry of the near horizon. What about when we go very, very far from the black hole? When we go very far from the black hole, we see also it looks like space-time, it looks like flat space-time, but here's the metric that we would see. We take the Schwarzschild metric, the good old Schwarzschild metric. Let's write it down. ds squared is equal to 1 minus 2mg over r dt squared plus 1 over 1 minus 2mg over r dr squared. And now we go far from the black hole, which means r very large. What happens to this when r is very large? This is dt squared, excuse me. It just becomes dt squared plus or minus dt squared plus dr squared. Okay. R and rho, far from the black hole, r and rho are the same thing. Once you're way far away from the black hole, the proper distance to the black hole is approximately just r. It's only near the black hole that r and rho are very different from each other. But when you're far from the black hole, radius is just radius. Distance from the horizon is basically the same as it would be in flat space. So far from the black hole, rho and r are basically the same thing. This factor here is not interesting. It goes to 1. This factor down here also goes to 1, and we just get minus dt squared plus dr squared. All right, so far from the black hole then, ds squared is minus rho squared. But let's write, sorry, not minus rho squared, excuse me. I just want to write dt squared. I just want to write dt squared because there is no interesting factor. So what is dt squared? Dt squared is 16 m squared g squared d omega squared. What I've done here is just multiplied by 4mg so that t is equal to 4mg times omega. That's this piece here. And then the other piece is just plus d rho squared. The d rho squared is just this over here, making use of the fact that rho and r are the same thing far from the black hole. So look what's happening, that near the black hole, the only interesting difference between these two is not in the d rho squared term, but it's in the time term. Omega is a kind of time. It's related to time through this equation over here. And on the one hand, near the black hole, there's a factor rho squared. When rho is very, very small, it means that time runs very, very slowly. Near the horizon of the black hole, there is very little proper time in any appreciable d omega. But far from the black hole, this is what the formula says. Okay, this is curious. What's going on? How do we think about this? What kind of geometry? It's a little hard to envision. In fact, it's quite hard to envision. But as you move away from the horizon of the black hole, this here thing goes to this thing. I'll try to give you the best picture I can of what this geometry is like.
Minus 16?
Yeah, minus. All right. Let's come over to here, to this picture over here. It's much easier to understand space than it is space-time. So let's come back to this picture, and now imagine a geometry which has the following property. Near the origin, it looks like rho squared d theta squared plus d rho squared. But far from the origin, it looks like instead of rho squared, let's just say 16 m squared g squared d theta squared plus d rho squared. Very similar to what's going on over here, except we're not dealing with space-time, we're dealing with just ordinary space. What kind of geometry is this? So let me show you what it looks like. Can you guess what it looks like? This is, I'll show you. Near the origin, it looks like polar coordinates. Let me draw this plane on its edge, like this. Here's this plane, drawn edge on. As I go around theta, I just go around here. Near the origin, it looks like the plane. But now as I move away from the origin, what happens, look at it, instead of having this rho squared here, we just get a constant squared. The meaning of that is that the distance around theta, between two neighboring values of theta, instead of depending on rho, just becomes constant, becomes 16 m squared g squared. I'll show you what it looks like. It looks like a cigar. It looks like a geometry that looks like this. Where the distance around the cigar at this end here is, well, theta goes from 0 to 2 pi. So the distance around the whole cigar in this direction, the cigar band, is 4mg times 2 pi. Theta goes from 0 to 2 pi as you go around. And okay, so that's what's at this end. On the other hand, very near the origin over here, it really just does look like polar coordinates. Theta goes around, looks like polar coordinates. Very close to the tip of the cigar looks flat. Any geometry in the vicinity of a point looks pretty flat. But as you go out and as you move around this point here, close to the tip of the cigar, this is the metric. Far from the tip of the cigar, the distance around the theta axis does not depend on how far away you are. Same here. The distance in omega, when you're far away, doesn't depend on rho. When you're close in, the distance for a given omega does depend on rho. The main message here is that this is a curved space. It's a curved space with a curvature near the horizon. And how does that curvature depend on m and g? Well, the distance around this cigar gets very, very big when m and g get big. So when the mass gets big, the distance around the cigar gets big, and that means that the curvature at the tip of the cigar gets less. The bigger the mass is, the less curvature that you have at the tip of the cigar, the less curved it is. A small mass would look like this, highly curved at this end. This is also true of the Schwarzschild black hole. Highly curved when the mass is small near the black hole tip, near the horizon. This point is the horizon. It maps or becomes this point over here. So you can get some feel for what this geometry is like by looking at its ordinary space version. But still, I think that's not completely satisfying. It just is what it is. It is what it is. Here's the geometry. The coefficient of the omega squared varies from near the horizon, where it's rho squared, to far from the horizon, where it just becomes a number, the number being 16 m squared g squared. And that's really all you really need to know about the black hole. What is this factor here? We look at given angular separations. The factor in front of the d omega squared tells us how much proper time there is from one omega, let's call this omega equals 0, and let's call this omega equals 1. Near the horizon, very close to the horizon, where rho is very small, the proper time distance between omega equals 0 and omega equals 1 is very small. Okay? So near the horizon, as time flows, as omega flows, very, very little proper time between neighboring values of time. Okay? Far from the black hole, neighboring values simply have time differences, which are just this number here, which is nothing but dt squared. Okay, so clocks, this is a statement about clocks. Clocks far away from the black hole behave exactly as you would expect. They read this time here. Clocks very close to the black hole read rho times omega. Rho times omega. Omega is a kind of time variable, but it scales differently close to the black hole. All right, that's what a black hole is like. Now, again, outside the black hole corresponds to rho greater than 0. Rho greater than 0 is all of these curves here. Here's rho equals 1, rho equals 2, rho equals 3, rho equals 4. That's outside the black hole. Anybody who's stationed at rest outside the black hole, if you were at rest outside a black hole and just let go, you'll slowly fall toward the black hole if you're far away. If you're very, very far away, it'll take a long time, but it doesn't take much effort to stay out of the black hole. You can orbit around the black hole. You can just have a little jet propulsion device that can keep you out of the black hole, and that's moving along one of these trajectories here, just staying a certain distance away from the black hole. All right. On the other hand, once somebody passes through, we'll now call this the horizon, the event horizon. This is the bifurcate horizon. This is the event horizon. Once you pass past the event horizon, you cannot send a message to the outside world. That's the character of the black hole. That's what makes it a black hole. Good.
On that diagram, the speed of light is a straight line?
Oh, speed of light, radial speed. Radial light waves always move on 45-degree axes. In any drawing I ever draw, unless I tell you otherwise, and I may tell you otherwise sometimes, but the speed of light is a 45-degree line, right? So a light ray falling in that way, a light ray trying to get out that way, but it won't get out. So light rays can fall in, but they can't fall out. All right, what about the singularity? Let's go back to the Schwarzschild metric, which I've erased off the blackboard someplace, and write it down again, and see if we can trace. Well, first of all, let's redraw this diagram.
Can I ask a question about the terminology you're using? You're saying when the light ray falls in.
Light ray shines into the black hole. Go ahead, what are you going to ask?
Because does the light ray stay at the horizon and right across the horizon of the black hole? It doesn't actually fall in?
We'll see.
Okay.
Well, we can answer that right now. Here's Bob. Bob is riding on his trajectory. He's riding on his world line. Let's move him out a little bit. Okay. Bob is quite far from the black hole. Here are omega equals 0, omega equals 1, omega equals 2. What about the Schwarzschild time? You know, the usual time that Bob measures on his wristwatch. He measures Schwarzschild time, the t. Well, t and omega are basically the same thing except for a factor of 4 mg. So this would be his time equals 0. This would be his time equals 4 mg. This would be his time equals 8 mg, and so forth. So riding along here, Bob is looking at his wristwatch, and time is ticking off. There's an infinite number of ticks along his trajectory. He never falls into the black hole. Why not? Because I tell you, he doesn't fall into the black hole. He stays outside. He's orbiting it. Right? So he stays at a fixed proper distance. That means on a fixed hyperboloid here. And he looks back. Let's draw in Alice. Now, Alice doesn't have to be Alice. Alice could be a proton. It could be a photon. It could be anything falling or moving in this direction. Let's say a photon. You asked me about a photon. Here's a photon. That photon moves 45 degrees, and it sure looks to me like it passes the horizon. What about Bob? What does Bob say? So Bob's wristwatch reads off time. Time infinity is way, way out there. So he looks back from wherever he is. Let's get another color onto this problem. Red. Bob looks back, and he sees the photon over here. Why do I say he looks back? He looks back and he sees the light coming to him from well, light doesn't usually come from, yeah. Strictly speaking, Bob can't see this photon. The photon's going the other way, so let's not make it a photon. Let's make it Alice, okay? It's Alice. Alice is falling through. She's waving her hand as she falls through. And Bob looks at her. Here's her waves. Let's make them closer together. She's waving pretty rapidly. Along her world line, she's waving. Hi, Bob. Bob is looking back, and from this point, he sees Alice over here. We all see each other slightly in the past. It takes light time to get to us. So Bob sees Alice over here. Next, after another interval of time, he sees Alice over here. She's waved a certain number of times. Bob sees Alice wave a few more times. Bob keeps looking back. He keeps looking back. And according to him, each one of these measurements, each one of these observations is separated, let's say, by 1 second. Each one is separated by 1 second along this trajectory here. But look what happens. He sees fewer and fewer of Alice's waves per unit time. Eventually, as he gets way out there, a huge amount of time, of his time, transpires, but he only sees one wave. And then, as he goes further and further into the distant future along his accelerated trajectory, he sees the last wave right over here, but he never sees Alice cross the horizon. He cannot see Alice cross the horizon. So, from his point of view, Alice waves slower and slower and slower, and eventually just comes to a frozen halt where she appears to be frozen on just outside the horizon. How close to the horizon? Well, let's take that point over here. That corresponds to some hyperbola, and that hyperbola tells you how far she is from the horizon at that point. So that's Alice. Yeah.
So from Bob's perspective, he's going to see Alice in the exact same place, right?
He sees Alice.
She's frozen in the exact same place,
Yeah.
right? So that means there's some information that's being
Well,
retained.
This is a classical picture of the black hole. There's not accounting for the quantum mechanics of the black hole. Right. So from a completely, look, what would Bob actually see? Imagine Alice, you see her wavings getting slower and slower. She's sending out light waves. It's the light waves that Bob sees. How does she send out light waves? She sends out light waves by taking electric charges and wiggling them, right? It's our atoms that do the wiggling, of course. Bob sees Alice's wiggles of her charges slow down. What does that say about the light that Bob sees? At first it's optical waves, then it becomes infrared. Eventually it becomes long wavelength radio waves. Bob doesn't see Alice anymore, but maybe his long wavelength radio can pick up a few of her waves. But then her wavelengths get so long, or the frequency gets so low, that Bob just doesn't see anything. So really, strictly speaking, Alice just fades away. She just fades away from Bob's point of view. Her radiation goes from being optical radiation to being thousands of miles long, not infrared, but radio waves, and even longer. So Alice fades away. How about Alice? What does she see? You might think maybe that means that Alice sees Bob speed up. So let's look at what Alice sees.
One quick question
Yeah.
before you get to. But as Alice is fading away, she's also getting smaller, right?
More squat.
Yeah.
If I'm falling onto the horizon, I slow down from your point of view. I don't get squashed this way, I get squashed this way. Right. It's a form of Lorentz contraction, but yes, that's what it sees. How about Alice? What does Alice see? Alice looks back. Let me draw a little cleaner Alice here, now in green. This is Alice's clock. Alice's clock doesn't do anything very special. She looks back and sees Bob, and she sees Bob, and she sees Bob. She sees, even after she passes the horizon, she sees Bob. What she sees is Bob accelerate away from her. Bob doesn't disappear from her perspective when she crosses the horizon, not at all. What does happen is she sees him accelerating away from her. Okay. So that's what happens to, that's Alice's view of things. She doesn't see Bob speed up. Bob sees her slow down, but she doesn't see Bob do anything special when she passes the horizon. Bob looks perfectly normal. She can send him, he can send her signals. He can send her signals from, but she can't send, he can send her signals. That goes this way. He's sending her signals, but she cannot send him signals. So it's a kind of one-way barrier. The horizon is a one-way barrier.
Isn't his light blue shifted?
No, actually not. Well, I mean, as seen by her?
As seen by her.
No. As a matter of fact, since he's accelerating away from her, her light is redshifted. His light is redshifted. He's more and more Doppler shifted toward the red. So, no.
His light is redshifted. His light is redshifted.
She sees him redshifted. He sees her redshifted until she just fades away. Okay, but it's completely asymmetric. All right, that's the picture of Alice and Bob falling into the black hole. Yeah, question. Yeah.
Does this apply to gravitons?
Yeah.
So Alice's gravitons are never seen by Bob
Right.
and her colleagues,
Right.
and all the infinite number of colleagues.
Yep. Gravitons are just particles like photons. Much harder to see, but much harder to detect, but still, conceptually, they're just photons. Or similar to photons.
But
then,
once Alice falls in, the mass increases, so the radius increases.
Once Alice falls in what?
Once Alice falls into the black hole,
Yes.
like we've increased the mass of the black hole, so the radius does increase a bit.
We'll come to that. We'll come to the increase of the mass of the black hole. Yeah.
If
we're
the-
going to talk about that.
if the gravitons can't escape, I would think then just like the black hole not only dark, it would be gravitation free, but that's not.
No. No. You don't feel gravitational fields because there are real, genuine gravitons coming at you from the Earth.
I thought that was the force, the field that carried the gravitational forces.
Virtual gravitons, which have no trouble exceeding the speed of light.
Sorry?
Virtual gravitons have no trouble exceeding the speed of light. What's true is, I've been standing here a long time. You can feel my gravitational field. What in a sense you're feeling is the gravitational field that was created sometime in the past relative to you. Now I move suddenly. The constraints on the speed of light of gravitons tell you that you cannot see me move, or you won't feel me move. Your gravitational field that I exert on you will not change until light gets a chance to get to you.
Doesn't
That's
that
all it
say,
says.
doesn't that they say that light and that gravitational field moves at the same speed?
Yeah. Everything I just said is also true of electromagnetic fields. If I were highly charged, and you were also highly charged, we might either repel each other or attract each other. You're supposed to laugh at that, but, right? And that would be a sort of steady state situation. But if I suddenly moved, you would only detect my field changing by after light got to you.
At light speed. At light speed. I mean,
Right.
but you just said virtual gravitons go at infinite speed. I don't know the distinction between virtual gravitons and what you've just described, I guess. If it's not germane, then that's fine.
It's not germane. Okay. Yeah. Yeah. Virtual gravitons you can just think of as the units of gravitational field which make up the static gravitational field of a stationary object, right? They don't have to escape from the black hole. They're there. They're there. They're there. Okay. Let's talk about this puzzle of what you see when you watch your feet fall through the black hole as you're falling. Everybody always gets confused about that. What happens when I see do I see my feet pass through the black hole horizon. How can I see my feet pass through the black hole horizon? All right, so let's set up that problem. Alice is falling into the black hole. Here's her feet. Her feet fall through first. Okay, she's falling feet first. Right. Here's Alice's feet. I'm not going to try to draw feet. Yes, I will. Here's her feet. No, I can't draw feet. Okay, here's her feet. That's the world line of her left foot. The world line of her head is over here. It follows her in, falls in later. So here's Alice's feet, here's Alice's head. Alice is looking at her feet. Okay? So at this point over here, she certainly sees her feet. But she sees her feet over here. She doesn't see her feet at the instant when she looks at them. She sees her feet slightly in the past. Alice sees her feet from here. There's Alice's foot. Alice sees her feet from here. Alice sees her feet from here. And she sees them from here. Yeah, right. She looks back and sees the light coming to her from her feet. Here's the light coming to her from her feet along a 45. My 45-degree angles are not particularly accurate, but they're supposed to be. All right. So light comes from here. Alice sees it. She's wiggling her toes, and her toes are electrically charged, so they're sending light. Sees light here. Sees light here. Sees light here. There's no point at which she doesn't see her. Feet. Of course, she doesn't see her feet from this point at the same time. From this point over here, she doesn't see her foot at that same instant of time. She sees her feet from slightly in the past. So there's nothing special happens when she passes through the horizon. Okay, now suppose that her head stays out of the black hole and her feet, which have already passed through, too late, her foot has passed through, but she decides at the last minute, no, I don't want to go there. Then what happens? Well, that's bad. That's not good. Let's see what happens. Alice's head now takes off and separates from her feet. Okay. There's no way that she can avoid her feet being torn off by the acceleration. So to keep out of the black hole, she has to accelerate away from her feet. Now, her feet might get pulled. Okay, her feet might get pulled. But they can't get pulled fast enough to keep up with her. It looks like they're keeping up with her, but they're not. And the reason is the following. As Bob moves faster and faster, Bob is accelerating away from the black hole. He's not really accelerating, he's standing still. But when you stand still in a gravitational field, it's the same as accelerating. So Bob is accelerating away. Think about this now. Think Bob accelerating away, and the distance to Alice, or Bob and Alice, this is now Bob and Alice, Alice is dragging behind Bob at a fixed distance in your reference frame. What is it like in Bob's reference frame? If the distance to Alice in your reference frame at rest is fixed, and Bob is going faster and faster, what does Bob say about Alice? Well, she's not so much going the opposite way as she's just getting lost. She's getting separated farther and farther because of Lorentz contraction. So Bob says, oh my goodness, Alice is getting farther and farther away from me, even though the observers at rest say that Alice is a fixed distance away. She can't get closer because she can't get past this light cone. She can't get up to the speed. She can't go faster than the speed of light. Right? So eventually, from Bob's point of view here, Alice just drags further and further and further behind. And if it happens not to be Alice and Bob, but happens to be Alice's head and Alice's feet, then Alice's feet are just stretched away from her until bad things happen, until they break. So once Alice's feet are behind the horizon, she has two alternatives. Fall in with them, no problem, nothing unusual, or stay out of the black hole and she will be defeated. What? Defeated. Oh, that was good. Now, so far, we haven't discussed anything about the singularity of the black hole. So let's start to talk about the singularity of the black hole. Where is it on this chart here? Where is it on this diagram? Let's clean up the diagram again. Let's get rid of the head and the foot. And let's come back to the Schwarzschild metric. Let's rewrite the Schwarzschild metric. dt squared times 1 minus 2mg over r, with a minus sign, and with a plus sign, 1 over 1 minus 2mg over r, the r squared. And then there's another term, r for the angular coordinates. Let's suppress that, not worry about it. The term which has the negative sign is always time. You always recognize time, or the time-like variables, by a minus sign in front of their metric. You recognize the space-like variables, ordinary space, by a positive sign in the metric. But something happens when r crosses 2mg. When r is greater than 2mg, this is positive. 2mg over r is small. 1 minus a small number is positive. But when r gets smaller than 2mg, suddenly the sign changes here. The sign also changes here. It means that somehow r is becoming a time-like variable and t is becoming a space-like variable. That this does not mean that anything dramatic, doesn't mean space turns into time behind the black hole horizon. This is a feature of a peculiar set of coordinates. When you go past the horizon, the coordinates interchange. What's happening here is something like this. If you were to move in along a surface of constant time toward the horizon, you would get to the horizon. R would be decreasing, R decreasing, 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 until it gets to 2mg. And then where does it go from there? Then suddenly, when r gets past the horizon, it becomes a time-like coordinate. R goes up that way. What about if omega is a little bigger, or t is a little bigger? So we come in also to the horizon. This is omega equals 0. This is omega equals 1 unit of time later. We also come in and we hit this point here, and then these coordinates, these Schwarzschild coordinates, which are peculiar coordinates, suddenly make another turn and go off here. So they're funny coordinates. There's nothing special happening over here. It's just a choice of coordinates that you've used where on one side of the horizon, r is a space-like variable. On the other side of the horizon, it's a time-like variable. And vice versa. Time turns into space, space turns into time. But nothing really is happening at this point. It's just an ordinary generic point of space-time. Okay, now let's go to where the singularity lies. The singularity is at r equals 0. That's a nasty place. There's something very dramatic happening there. Tidal forces become infinite. Curvature becomes infinite. All hell breaks loose at the singularity. That's r equals 0. Well, as we start coming in, we go to r equals 2mg. That's not 0. Then we continue along the r-axis. Think of it as the r-axis, but the r-axis makes a right-angle turn until we get to r equals 0. And that's over here. This is r equals 0. We do the same thing on another curve, and we come to r equals 0 over here. If we connect all the points that correspond to r equals 0 together, it looks like this. It looks like a hyperbola. It is a hyperbola. That hyperbola is the singularity. Let's draw it having a nasty, wicked points because it's highly curved and very unpleasant. You sort of thought originally that the singularity was a place. A place means a place is a vertical world line. But it's not a place, it's a time. Moving along here, the singularity occurs after a certain amount of time. Not really a place, it's a kind of time. There's the singularity. That's the nasty place. Okay, let's think about now poor Alice, who has fallen behind the horizon here. She's over here. Where does she go next? She wants to escape the terrible fate of falling into the singularity. She can try to get out, or she can try to go that way. Either way, she cannot escape. There's no way that she can, without exceeding the speed of light, she cannot escape the fate of falling into the singularity. So that's another property. Once you pass the horizon, that's it. You have no chance but to fall into the singularity. Not only can't you communicate to the outside, but you're doomed. You're doomed by the singularity. And that is one more feature of the black hole. Now, the mathematics of this metric, now we come to a real curiosity, but it's a mathematical artifact, which we're going to find doesn't really mean anything physical, but still is a mathematical artifact. This geometry here is the same if you turn time to minus time. In fact, these coefficients here don't depend on time altogether. And what happens to dt squared if we take time to minus time? It stays the same. This metric here is what a physicist would call time reversal invariant. It looks the same going forward as going backward. Well, that's a little bit peculiar because you can see over here that sort of forward in time, there's a singularity. What it implies is that there must be a singularity also in the past. And if you study this metric in its mathematical detail, you'll find out that what it really represents is a time-symmetric situation with a singularity in the past and a singularity in the future. Now, Alice doesn't have to worry about the singularity in the past. There's no way she can get back to the past. You can't get back to the past. She has to worry about the singularity in the future. Okay? She's going to fall into the singularity over here. But let's just think of Alice's history for a moment. Incidentally, the meaning of saying that something is time reversal invariant is the same as saying that a particular history, if you were to run it backward, if you were watching the events taking place and you were to run them backward, meaning to say you would take a film of them and run the film backward, that the backward film would also be a possible history which makes sense as a solution of the equations of the theory. That's what it means for something to be time reversible. The equations of general relativity are completely time reversible, so anything that can happen forward can also happen backward. So let's think about what that means. Here's a history. Alice jumps into the black hole and winds up on the singularity there. As she passes the horizon, Bob loses track of her, can't see her. Well, if that's a possible history, then we should be able to fold it over and say there's another possible solution of the equations in which Alice is created at the singularity and jumps out of the black hole. Well, there's Bob looking back at the black hole. Oh, she has no trouble going this way. No trouble at all. She can't cross out from here. Well, the time reverse of that has nothing to do with her ability to get out of this. This is called a past horizon. Alice has no trouble at all getting out of the past horizon. It's simply the time reversal of the statement that Alice had no trouble falling into the horizon. The time reverse of passing out, here's the horizon. Time reverse of passing in is passing out. So if she can pass into the horizon in the future, she can pass out of the past horizon in the past. What does Bob see? Bob looks back and sees something silly. He sees a Alice ejected out of this black hole. That's silly, of course, right? I mean, that's nonsense. Right? So there's something wrong with this picture. We're going to find out what it is. Hmm? No. Here's Bob over here. He looks back. He actually seems to be able to see the singularity. That's in itself a little bit annoying. He looks back and he sees the singularity. Oh boy. And then he suddenly sees Alice jump out from the singularity. What is that called? Anybody know what that's called? This nonsensical configuration? Fiction. Yes, it is. Well, the first thing is, yes, it is possible. Is it likely? No, it's unlikely. This is called a white hole. A white hole. This is what a white hole is. Now, white holes don't exist. They don't really make sense.
Doesn't Bob also have a history going in reverse at this point?
No, Bob is out here. He's just doing what he ordinarily does. This is fictional. This is not something that makes a lot of sense. It's about as likely as well, what's a good example? You evaporate water from a puddle into into space. Instead, you see water materializing from space. Well, this can happen, can't it? It's called just condensation. I better be careful. All right. A bomb explodes. A bomb explodes and sends garbage all over the place. Right? That's a possible history of, let's say, Newton's equations for a bunch of particles where you start with a bomb, you know, one of these old-fashioned bombs that Bolsheviks carried around with a fuse, and like my grandfather would have had, I'm sure. And you wait a little while, boom, and stuff gets scattered all over the place. You'd be pretty damn surprised to see a bunch of stuff flying inward, reassembling the bomb, and doing it very delicately so that eventually it just had a little bit of a flame at the end of it. That doesn't happen, right? It's not going to happen. But wait a minute, it's a possible solution of the equations of Newton's theory. Newton's theory is completely time reversible. Okay? So what's wrong? Both are possible, but we know very well that one of them is not possible. Okay, just to throw words doesn't help. Yeah, it's entropy and it's... One of them is clearly extremely unlikely. The other is rather likely. Okay? They're both possible. With the inverse process, where stuff comes in and creates the bomb, all you would have to do is move one molecule a tiny, tiny fraction of a molecular distance in the incident state to completely undo the ability to create the bomb. It's extremely unstable, the backward trajectory. It's sort of like, imagine I have a very high mountain that comes to a point. It's very easy to roll a ball off the top, starting at rest. Just give it the tiniest little kick. Where will it go? It'll fall down the mountain. The probability that it will fall down the mountain is extremely high. The reverse trajectory is possible, throwing the ball up to and just getting up to the top, but extremely unlikely. The tiniest little bit of error, and you'll wind up missing the top. Another example. Everybody here play pool when they were kids? Billiards, you know? Yeah, of course you did. You start with all the billiard balls, all the balls racked up in a triangle, perfect triangle. How many of them are there? 15. Right. And you take a cue ball, you give it a good hard shot, and they go scattering all over the place. High probability that they'll just scatter all over the place. It would be rather amazing to see 15 billiard balls, even if we didn't worry about friction on the table. It would be rather amazing to see 15 billiard balls come together and form a perfect triangle with the cue ball going out that way. Pretty unlikely, right? But both of them are solutions of the same equations. So both are possible from the point of view of the equations. But the difference is that if you started those 15, 16 balls in a configuration which was just perfect so that they reassembled into the triangle, and then the tiniest little error, you would miss the triangle completely, and all you would make would be a table full of billiard balls going in random directions.
Yes, but also isn't it just as unlikely that you would have precisely the same thing going the other way every time you did it?
Yes.
In other words, each of these is equally unlikely.
Yes, yes, that is correct. But you know, if you were just to say, I'm watching this thing, and what I see is billiard balls scattered all over the place. Yeah, if you did it over and over and over again, you would get more or less the same pattern every time of billiard balls scattered all over the place. And unless you were following the billiard balls carefully, you wouldn't notice there was particular differences. But you would notice if the billiard balls came together and formed a triangle. So yes, you're right. I mean, I think your point is any given configuration is very unlikely. Right. All right, that's where entropy comes in. But what Bob is seeing here, and we're ultimately going to understand this in terms of the entropy of the black hole. But what Bob is seeing here, what we now understand, is he's seeing one of these very, very unlikely processes. Not an impossible process, but unlikely, where a black hole just sitting there suddenly spurts out a full-fledged version of Alice. Very unlikely. But not unlikely that Alice falls into the black hole. So it really is very, very much the same thing. We're going to find out that this is one of the aspects of black holes that has to do with their entropy. We've already discovered black holes have entropy. They're in thermal equilibrium. They have thermal properties. You could say the same thing about a pot of hot water. What's the likelihood that if you drop an ice cube into a pot of hot water, that it will form a melted configuration with the water, or just getting a little more water in it and filling up the pot a little more? Very high, right? What's the probability to sit and wait and watch that pot that an ice cube will get ejected out of it? But both of them satisfy the same equations, both of quantum mechanics and classical mechanics. So in that sense, they are both possible. It's the same thing going on here. The horizon of the black hole has entropy, just like the pot of water, hidden information. Very rarely will the entropy of the black hole, of the pot of water, assemble itself into an ice cube. Same thing here. Very rarely will the garbage on the horizon of the black hole assemble itself into ejecting Alice.
Is that probability all a quantum mechanical probability, or is it something?
It could be both. It's a combination of quantum mechanical and thermal. Thermal fluctuations and quantum mechanical fluctuations. Both are there. But in the case of the hot water, of course, it's mostly thermal. Right. Okay. Let's take a 5-minute break. And then we're going to talk about Penrose diagrams, and we're going to talk about actually making black holes, how you actually make a black hole, and why half of this diagram, namely the bottom half, is completely unphysical. It's not something you ever really have to worry about. The bottom half, which is the peculiar half of the white hole. Yeah. Michael asked me a question, and I realized when he asked the question that I was using a bit of jargon, so let me just clarify the jargon. I told you that rho was proper distance from the horizon. The jargon there was proper distance. Let me just remind you what proper distance means. It is a piece of jargon. It's similar to proper time. What does proper time along a observer's trajectory measure? It measures wristwatch time, right. But it's wristwatch time along a curve, right. All right, now we have over here Bob, and let's take Bob right at time equals 0. He draws the straightest path he can to the horizon. In this case, a straight line. What does it mean to say that this is a given proper distance away from the horizon? Yeah, it's the distance measured by real yardsticks or meter sticks in this room. We don't allow yardsticks in this room. We allow meter sticks. Distance measured with honest meter sticks. Okay, that's all it means. That to say, now, little r, where is it? Little r up there, I think I've erased it. Little r over here does not measure proper distance. It's just a mathematical coordinate which is not proper distance. It doesn't measure real meter sticks distance. Rho is the thing that measures real meter sticks. So I apologize for jargon, but sometimes I forget. Okay. Now let's talk about Penrose diagrams. Penrose diagrams are great. They really are the way to understand all kinds of things in general relativity, and they're easy. They're easy to think about, easy to draw, a little bit difficult to actually work out in detail, but we don't need to work them out in detail. Let's draw space-time on the blackboard. In particular, let's draw just ordinary flat space-time on the blackboard. Well, we don't have enough dimensions on the blackboard to draw 4-dimensional space-time. So let's pick out 2 coordinates. One will be time, and the other will be distance from the origin. Now, this is ordinary flat space-time, so it could be t and rho. Right? Time runs vertically upward, t, and rho is just distance from the origin here. So it runs sort of this way. Here's the rho axis. We can make a grid out of this by chopping up the time axis into intervals and then extrapolating them horizontally. And we can make a vertical grid. So the first point here is rho equals 0. Incidentally, nothing to the left, because by definition, rho is always positive. It's the proper distance from the, it's a sort of polar coordinate kind of coordinate. So it's always positive. And here it is. Here's all of space-time. This is rho equals 0 along here. Rho equals 1, rho equals 2, rho equals 3. Here's t equals 0, t equals 1, t equals -1. Time can get negative in this picture. And this is the history of the whole universe. How about light waves? Let's take a light wave that comes in from the remote past, comes in, hits the origin. What happens after it hits the origin? It just goes back out. It's not really bouncing off anything. It's just, here's the origin. My fist is the origin. It just goes right through the origin. But in polar coordinates, it comes in and goes out. So there's a light wave that comes in and goes out. A later light wave might come in later and bounce out, and so forth. Again, that's the history of the world on a small blackboard. But it's not the history of the whole world. The blackboard isn't big enough to describe the whole world. The whole world meaning all infinite distances out to infinity and all infinite times from minus infinity to plus infinity. So what relativists do is they make coordinate transformations. That's what relativity is all about. It's about coordinate transformations. But in particular, coordinate transformations which take the whole expanse of space and time and simply squash it by coordinate transformation onto a finite region of the blackboard. What you get is called a Penrose diagram. There's a rule, and the rule is that however you draw the Penrose diagram, basically only two rules. The first thing is use coordinates that gets the whole thing onto the finite blackboard. Squish it and squash it until you get the whole thing on the blackboard. But subject to the rule that light rays, radially going light rays, always move at 45-degree angles. This can be done for a very large variety of geometries, that you can squish it down in such a way that the light rays continue to move at 45 degrees. The result is called a Penrose diagram, and don't worry about the mathematics of how you derive the particular Penrose diagram. Just learn to read them, because they're easy to read. Here's what it looks like. Here's what the Penrose diagram of flat space looks like. There's the time axis, but it doesn't go from minus infinity to plus infinity. Well, it does, but we draw the whole thing between some point in the past and some point in the future, and that's the whole time axis. The space axis also goes out to some point. That's really r equals infinity or rho equals infinity, but we squash it in. And the rest of it is just a triangle in here. There it is. All right, let's see if we can take this grid and replot it on here. Start over here and work your way outward. That's t equals 0, and work your way outward. Here's rho equals 1. Here's rho equals 2, rho equals 3, but we've got to crowd an infinite number of them into here, so they're going to crowd up like that. Likewise, let's take time. Time 1, and they're going to crowd up as we go up here, and likewise down here. Let's try drawing this grid. Time-like lines, vertical time-like lines, all go up to time infinity. That's up here. That's time infinity up here. So all these vertical lines look like this. More and more and more of them out here. What about the horizontal lines? They all go out to rho equals infinity. That's all over here. It's all been squished or smushed into a point over there. And it looks like this. Curved. Okay, what about light rays? In particular, light rays that are aimed from far away toward the origin. Light rays come in from, first of all, they move on 45-degree lines. An incoming light ray would look like that. That would be the image in this diagram of the light ray, which came in like this. It bounces off the origin and goes back out. You could have earlier light rays that came in earlier and bounced back earlier. All light rays all incoming light rays originate on this side of the triangle. Now that's really way, way out at infinity, way down here. All outgoing light rays pass out of the diagram up here. That's just asymptotically far away in that direction. What about all time-like lines? Time-like lines are these observers, for example, these people who are standing still. They might be moving a little bit. They all wind up here. Where do they come from? They come from here. If you walk out, you can't walk out, but if you imagined moving outward along one of these timelines here to larger and larger row, you would eventually get over to here. This diagram and that diagram are the same diagram. This one has just been smushed or squished or whatever your favorite word is so that it can all be drawn on the blackboard, but subject to the constraint that the speed of light stays, the light rays move at 45-degree angles. This is called a Penrose diagram. This is the simplest Penrose diagram, and that's all it is. What else is there to say about this particular Penrose? Yeah.
Are those light lines squished to meet the corners of each of those squares as it goes through? Is that light line curved, or is it always a 45 line? As it passes through each of those squares,
Yeah.
is it supposed to be passing through the corners of each one as it goes through, so it would slightly curve as it goes through the graph?
I suppose it would be if it were. I suppose it would be if we drew it accurately. Yeah, if we drew it accurately, it would be. Yeah, this is true. Since it's passing through the corners here, right?
They all end up at 90 degrees to that, or to that outside boundary.
What about a light ray that was pointed not right at the origin, but missed the origin? How would you draw that? Well, we could come back here first and draw it here.
Well, you still have to be 45 degrees, so it would just intersect the higher lower point, wouldn't it?
No. It misses the origin. It never gets to the origin. So it comes in when it's very, very far away. It looks like it's aimed straight toward the origin. So it follows this route here. But it doesn't quite get to the origin. It comes into a distance of closest approach and then goes back out. So in fact, it would look like this. It gets to a distance of closest approach and then goes back out. But of course, there's angles involved. It doesn't come out in the same direction that it came in, but on this diagram, all right, it's the same thing here. A light ray that misses the origin just simply misses it. It never quite gets to it. It gets to a distance of closest approach over here and then goes back out.
But then it's not going at 45 degrees.
Yeah, I said radial light rays are drawn at 45 degrees. Radial light rays, ones which are aimed radially. Right. Ones which are not radial, you have to worry about specially. You have to take that into account. Okay, these different places, these different extreme limits of the Penrose diagrams have names. Of course, this is just the time axis. This one up here is called future time-like infinity. And it's usually just called T plus. Or T equals infinity. Yeah, how about just T equals infinity? This one down here is called T equals minus infinity. Time-like past infinity, time-like future infinity. What would you call this one? Space-like infinity. So this is rho equals infinity over here. What about these? Got a name for those? They're the places where light rays come in from. They're called light-like infinity. This one's called past light-like infinity. This one's called future light-like infinity. And for reasons that I have no idea, this was originally labeled I minus, minus for past, and I for the future. It was always labeled with a script I and known as scry. Scry minus and scry plus. Not my notation, so I don't have to apologize for it. Good. So that's the Penrose diagram of flat space-time. What about a black hole? what does a black hole look like? So to get to a black hole, let's redraw the diagram that we had earlier, and then try to see what it would look like if we did some smushing and squishing to squeeze it onto the blackboard. Okay, here's what we saw. We saw way out here, space-like infinity, that's way out, large distances from the black hole. Here are our time coordinates like that. Here was the singularity over here. There was also a past singularity over here. And we never discussed what was on this side. We never discussed what was on this side. I hesitated to tell you what was down here, but I eventually did. All right. What's on this side? Nothing of physical interest, but nevertheless, the mathematics of the Schwarzschild metric contains all of this. It contains an outside world over here and another outside world over here. This outside world is not the same as this outside world over here. You can't get a message from here to here, but the mathematics of Schwarzschild has both of these. We're going to find that half of this is really quite meaningless, but for the moment, this is what we found the metric looked like. This is what the geometry looked like. So let's ask what happens if we squish this. We're going to do the same kind of squeezing to get everything onto the finite plane. And I'm just going to draw it for you. I'll show you what it looks like. You'll recognize, or I think you'll recognize it pretty fast. Let's see. I need some guidelines to do it with. And I'll show you how to read it in a minute. Okay, let's start out here at r equals infinity. That's like r equals infinity or rho equals infinity. That's like way out here. Where do you think it ought to go? Way out here. Okay. This horizon over here, the bifurcate horizon, is right at the center over here. If I start at the horizon and go out to infinity, I can go this way. But I can also go along this line. This is omega equals 0. This is omega equals 1. Where is that on here? And notice, in either case, you wind up sort of in the same place. Same place, sort of. You wind up going out to r equals infinity. R equals infinity has all been smushed down to here. So where do you go? You go out to here. Likewise from here. That's the sequence of different time. Now let's look at different radial distances from the black hole. Different radial distances, I'm going to change color. Different radial distances, these are observers, if you like, who are stationary outside the black hole. They go up to time infinity over here, and they look like this. Okay. So this guy is 200 miles from the black hole. I don't know. This one's 500 miles from the black hole. That's 1,000 miles from the black hole. That's 10,000 miles from the black hole, and so forth. This one over here is hovering right above the horizon. And in fact, because he's trying to hover above the horizon, he must be accelerated. To hover above the horizon takes some rockets that are going to keep him from falling through. So that's him over here. The other side is a perfect reflection of this side. And this diamond here, that's the outside of the black hole. That's the outside of the black hole. That's where Bob lives. He lives out here, and if he doesn't want to cross the horizon, where's the horizon? That's this. Well, this is the bifurcate horizon. This is sort of the point of no return over here. What is this? That's the singularity. That's the image of the singularity over here. So here we go. Here's the singularity. What's this one? That's the past singularity, the one that was down there. Past singularity. Future singularity, past singularity. This is either r or rho equals infinity. Either way. How about light rays which come in? They come in from here, but now they don't bounce off the origin. What happens to them if they're radially inward? What happens? Do they bounce off and go back out? No, they fall into the black hole. They pass through here, and where do they wind up? On the singularity. Okay. There are light rays which go out to infinity. Of course, they could have been created by somebody here. One of these people here could have had a flashlight and sent a light ray out. But there are also mathematical light rays which begin on the past singularity and get radiated out. This is called t equals infinity. And it's the analog of the point up here. This is called t equals minus infinity. This is called r equals infinity. This is called past light-like infinity. This is called future light-like infinity. Okay. And that's it. That's the black hole. That's the Schwarzschild black hole in a nutshell. Drawn, all of space-time drawn on a finite piece of a plane. Radially moving light rays, always 45 degrees. From this picture, you can see a lot of what of the properties of black holes. Well, we've talked about them already. We've talked about what happens when Alice falls in, when Bob stays outside. Here's Bob. Here's Alice, except here Alice is a photon, but if Alice was moving more slowly, but same thing would happen. And once you cross into this triangle here, you're doomed. You have no choice but to go to the singularity. Now, what is this region out here? That seems like a second world. It looks like the black hole. This is the source of a lot of science fiction. It looks like there are two worlds connected together by a black hole. A wormhole. Right. A wormhole. However, it's not possible to go from this world to this world because even a light ray, once it passed this horizon, would wind up over here. So they're completely out of communication with each other. Nobody on this side can signal anybody on this side. So from the point of view of anybody in this diamond here, this doesn't exist. Well, that's a little bit glib, isn't it, to say it just doesn't exist. In fact, the real story is a little bit different. The real story has to do with the way black holes are made in nature. This diagram doesn't tell you how this black hole was made. This black hole was sort of always there. From the remote past to the remote future, the Schwarzschild metric was there. So it's a black hole which is eternal. Black holes are not eternal. They're made by collapsing stars. So the next question that we want to understand is, how is a black hole made? Now, a black hole before there's a black hole, it's not completely empty space. Stuff was coming in. We can imagine, let's take an imaginary scenario. Some particles come in from very far away. They might even be photons. When enough photons come in to a region of space, photons have energy, therefore they have mass. Enough photons and mass, and therefore they gravitate. If you can get enough photon energy into a region of space, you can make a black hole. So we can start with, not with nothing, but with just a very diffuse cloud of photons coming in from far away. That's practically empty space. Looks a lot like empty space. Where's the diagram that represents empty space? That's here. That's empty space. No black hole, just plain empty space. Maybe with some photons coming in. After the photons come in, if they make a black hole, then later what we should see is the black hole. The question is, how do you put these together? How do you put this together in the past with this in the future to represent the assembling of a black hole? So we want to go through that. We want to spend a little bit of time assembling a black hole. To do so, I have to tell you a theorem. I think the theorem will do for tonight, and we'll go through the construction next time. But it's called, in Newtonian physics, it's called Newton's theorem. In general relativity, it's called Birkhoff's theorem. And it's a very simple fact about Newtonian gravity or about general relativity. It's easy to understand. Hard to prove. Let's begin with Newton's theorem. Newton proved this. It's a theorem about 1 over r squared forces. 1 over r squared forces can, such as the Coulomb force in electromagnetism or the Newtonian force of gravity, 1 over r squared forces can be described by lines of force. I'll just remind you about lines of force. Here's your mass. Let's say it's a point mass. And imagine lines of force coming out of it. The lines of force could also be flow lines of a fluid coming out of a source at the origin. It could be two-dimensional with fluid spreading out over 2 dimensions, or it could be a 3-dimensional source over here where fluid flows away from the source. And you draw lines of force. The lines of force begin on the charged particle or the massive object and just go out, and they don't end. They don't end, of course, unless there's another mass someplace or another charge someplace. But let's say there's just one mass. That's the and what's the rule for the either electric field or the gravitational field? The rule is at any point the gravitational field, I think I will draw the gravitational lines pointing inward. Why is that? Yeah, because gravity attracts. So it's pulling on things. So the rule is, at any point, the force on a test object points along the direction of the line of force that passes through that point. And what about the magnitude of the force, the magnitude of the gravitational field? It's proportional to the density of the lines. If you think of if space as being filled up with a network of lines, the closer they are together, the stronger the force. All right, so lines of force, it's an imaginary mathematical construction. You fill up space with these lines of force or lines of flow of a fluid. That is everything that you can say about the Newtonian field, gravitational field of a point object. If you put 2 point objects together, then you just add the fields, which is exactly the same as saying I have 2 sources of fluid. In this case, I guess this would be a sink of fluid because the fluid is flowing in. You have 2 sinks of fluid. The fluid is being pulled in, and so you have 2 sources, and you simply sum the field of both of them, which means you study the fluid flow of the 2 sources, juxtaposed. All right, if you work out that, you figure out the field of an arbitrary distribution of masses. Now, the Newton theorem is the following. It says, if I take a spherically symmetric distribution of mass, and I'm going to take a very simple case. I'm going to take a shell. The theorem is more general than what I'm going to say, but I'm going to take a shell. A thin shell, spherically symmetric, of mass. Here it is. You can think of every point on that shell as producing fluid. If you look on the inside of the shell, there is no flow. How could there be? Which way would the flow if you were inside the shell? Well, you might say it flows radially. By symmetry, it would flow radially. But if there was flow inside the shell, where would it go? There's no mass at the center. I'm assuming all of the mass is on the shell. There's no place for the fluid to go. So if there's no mass at the center, there can't be any radial flow. There can't be any flow at all. So the interior of a shell of sources of fluid has no flow at all in it, which is another way of saying there's no gravitational field at all inside a spherical shell like this. What about the outside? The outside has a flow which is radially outward. The lines of force look exactly as if they had emanated from the point at the center. And the total amount of flow is whatever the total amount of flow coming out of the shell is. In the language of gravitation, what it says is the gravitational field of a shell of mass m outside the shell is absolutely identical to a gravitational field of a point mass at the center. But inside the shell is no gravitational field at all. So inside the shell, exactly the same as empty space. Okay. Outside the shell, exactly the same as the point mass. There's a general relativity version of this. Incidentally, let me say something else. This is true even if the shell is time dependent. For example, as long as the total amount of fluid coming out of it is conserved. If the shell were to change size in a way that did not change the total amount of fluid coming out of it with time, it would still be true at any given instant the gravitational field inside the shell would be that of empty space, and the gravitational field outside would look exactly like the point mass. It would just be the place where you go from outside to inside, which would change with time. So in particular, if you had a time-dependent shell of mass which was contracting with the mass staying fixed, then outside it, you would see the point mass gravitational field. Inside, you would see nothing. Only the boundary between the two regions would change with time. The same exact thing is true in general relativity, almost the same thing. Close, not quite, but close. All right, so let me tell you what is called Birkhoff's theorem. And then the next time, we will combine Birkhoff's theorem with these two diagrams and put together the theory of how a black hole is formed. Okay. So get Birkhoff's theorem, remember it. All right, what does it say? It says if you have a spherically symmetric distribution of mass, what do you see inside the spherically symmetric distribution of mass? Exactly what you would see if there was no mass at all. Flat space-time, empty space, flat, Minkowski, whatever you want to call it, just the solution of gravity of Einstein's theory with absolutely nothing there, just good old empty space inside. What about on the outside? What do you see? You see a Newtonian gravitational field? No, not quite. What do you think you see on the outside? It's spherical mass, but what's the gravitational field on the outside? Schwarzschild. In other words, the metric on the inside is exactly that of flat space, and the metric on the outside is exactly that of the Schwarzschild black hole. We can write it. On the inside, we have good old the t squared minus the x squared, the y squared, the z squared, and on the outside, we have Schwarzschild. I'm not going to write it. I think I could have written the metric faster than I could have written Schwarzschild. Right. In other words, we piece together two things, both of which we know very well, connected together by a shell. How about the mass of the Schwarzschild solution? Schwarzschild solution has a mass associated with it. It's just the mass of the total shell. Does the mass of the shell change with time, even if it moves, even if the shell contracts? Does the total mass of the shell change with time? Why not? Well, supposing I tell you, supposing I just mutter the words E equals mc squared. Conservation of energy. Right. The mass, the total mass of that shell, even if the shell, and can the shell change? Of course the shell can change. You build yourself a shell, but the shell isn't strong enough to maintain itself against the gravitational field. What happens? It starts to collapse. As it collapses, the mass doesn't change, but the radius of it changes. What was inside was just good old flat space. What was outside was Schwarzschild, and the boundary between the two behaviors might change with time. So what we're going to do next time is we're going to take the flat space solution, that's the inside, and patch it together with the outside, which is the Schwarzschild solution. I'll show you how to do that, and in that way we will learn in a very simple example how a black hole is formed. We'll find that half of this diagram doesn't mean anything, but we'll come to it next time. So, formation of a black hole next time. Okay.
For more, please visit us at stanford.edu.